This is just an inaugural lecture. So thanks to Tomo for the invitation. Happy to be here in nicer Kolkata again. So the thing is that my job is really fun because I'll be just telling stories and proving part of the test is Tomo and Tomo. So they will do that job. So I'll start with where it all began more than 2,000 years back. So it started with Euclid, who wanted to prove that there are infinitely many primes. Of course, everyone knows what primes are. So I'm not going to the definition of prime. So Euclid proved there are infinitely many primes. I don't know when it was, more than 2,000 years. So there are infinitely many primes. And the idea of the proof was very simple. So assume there are infinitely many primes, take the product of all of them and add 1 to that. And the fundamental theorem of arithmetic says that you have a prime factor, and then you can check that none of those primes can be a factor of this. So that's the one prediction. So that shows that infinitely prime. Okay, and the topic of this Gyan course is zeros of the function. I have to tell you how this is related to the zeros of the function. So that's the main thing. So after 2,000 years, almost 2,000 years, Euler came up with a different proof of infinity primes, right? And what he did is he defined this series. So he looked at the series 1 plus 1 by 2 to the power s plus 1 by power s, 1 by 4 to the power s, etc. So in short form, we write this as sum of 1 by power s infinity running over positive integers. Euler took s to be a real number, and it's very easy to show that if you take s to be a real number larger than 1, then this is absolutely convergent, and it makes sense. Let's call it zeta. It's the famous zeta function named after Riemann, but not named much later after Euler. And the fundamental observation of Euler was that that this series can also be written as a product over primes. Product over primes, 1 minus 1 by p to the power s. And it's and again, you take s equal to 1 and show that this is also converting this product. And this equality that this series is equal to this one is just the fundamental theorem of arithmetic. That every integer, every positive integer can be written uniquely as a product of powers of primes. Right? If you do the geometric expansion of this one, you'll get all the powers of primes. When you take the product over all primes, you get all possible combinations. That will be evolving. That's the fundamental. Right? So this equality over here is what is called the fundamental theorem of arithmetic. And what was Euler's idea? So Euler knew that if you take s going to 1, right? So s here is a real number, so it's 0 to 1. But if I take s over here, then it's absolutely converting. But now I'm taking s going towards 1. The lift as s goes to 1, one can show very easily that this series diverges. So as the s goes to 1, theta is with infinity. Okay? And what does it mean? Now suppose if you have only finitely many primes, then this product will be finite. And then it will still make sense for s equals to 1 with this finite number. Right? So as s goes to 1, this product is equal to this series, but this series is going up, going to infinity. But if there were only finitely many primes, this is finite. Okay? That's a contradiction. Okay? So this will imply that infinitely many. So that's a different proof of infinitural prime. But it gives you much more than that.
Join group.
So suppose it takes a log of this product. So suppose you take log of then what you get? You get sum over primes log of 1 minus 1 by 54 is minus sign over there. And then if you take the expansion of the logarithm, then you get a sum over prime and the sum over positive integers k, and you have 1 by k. And now if you separate out the k equals to 1 part, then we have a sum over prime 1 by p to the power x plus sum over k is greater than 1, sum over primes 1 by k to the power x. And you can show very easily that this part, as s goes to 1, still remains finite. So as s goes to 1, this is still finite. But so that means since this is going to infinity, theta x goes to infinity, so not theta goes to infinity. So this goes to infinity, this sum, this plus this goes to infinity, this remains finite. After this goes to infinity. So from here you can conclude that if you take the reciprocal to the primes, then that is also infinite. So not only they are infinite in many primes, but if you take the reciprocal of the prime and add them up, it's infinite. So there are more primes than the squares, because if you take the reciprocals of the squares and add them up, then it's a finite number, like Spirit says. This is infinite. Right? So yeah. So that's so some Euler proved something much more than what. All right. Yeah. So later, yeah. So at this point, one can either go and talk about Dirichlet, or one can talk about Riemann. So let me talk about Riemann. So why is this called a Riemann defect? Okay, so Riemann wanted to prove something more about primes. So there was this conjecture of Gauss and then guy, which says that if you count the primes up to x, so take a prime and going up to x, then this is a synchronical equation like x by log x. And Riemann wanted to prove this. He wanted to not only prove that there are infinitely primes, but he wanted to count how many primes are there. Right? This, of course, gives you infinitely many primes. The number of primes is an case going against by log, it's just infinity. Right? But it's much more than that. And so Riemann's idea was to study this Riemann, this data function of a complex number. So let's take S to be a complex number. Before him, of course, Euler looked at the same series, but he was taking S to be a real number. Right? But you see, the real analysis and complex analysis are completely different. And the complex analysis have more structure. And as you know, there are many theorems in complex analysis which are not true or so let's see what happens. So this is my complex plane. That is plane. And following Riemann, we still write S to be sigma plus IP. So sigma is the real part, sigma, and P is the imaginary part. So that's it. This is my origin. So, and this is the line passing through 1. Yeah. So if I take a complex number S, say over here, sigma plus IT, where sigma is strictly larger than 1, then the same argument will show that if you take the absolute value, that will just reduce this sigma excess of S over here, and you still have absolute convergence. So in this region, in this half plane, this is the region of absolute convergence. Both for the series and for the curve. By the way, this series is called a Dirichlet series. This product here is called a wave. So the Riemann zeta function comes with a Dirichlet series expansion and also an Euler rule. Both of them are absolutely converging for sigma points. And from there, you can say that it's like a product like this. This is never vanished. Product of non-zero numbers never vanish. So here, theta is from that. Okay. And the fact that as s goes to 1, this is going up, boils down to saying that here something is going on. What Riemann was able to prove is one thing. He showed that the zeta is has analytic continuation in all of C except a simple pole at simple 1. So he showed that the zeta function will make sense whatever s you pick. It doesn't matter as long as s is not equal to 1. Okay. You can take s to be something over here with a sigma negative, or you can take s to be something over here between sigma between 0 and 1. It will still make sense. Though the series and the product will diverge, right? But it will have an identifier. And furthermore, it proved that if you complete the zeta function by multiplying an appropriate gamma function, okay, then there is a functional equation. The value of this at s is same as this value at 1 minus s. Right? And that means the half is the center of symmetry. So if you take any point s over here, the 1 minus s point will be just the reflection of that at half. S is 1 minus s, right? And the value at this point for this completed zeta function is same as its value at 1 minus. Right? And gamma function, of course, you know, is there. Very sharp gamma function for 1. So with the help of this functional equation, we can say a lot about what happens to the zeta function when the sigma is less than 0. Because this functional equation just takes this half plane, sigma less than 0, the half plane sigma greater than 1. So to study what happens over here, you just use the functional equation and come over here, and then use the property. So from there, we can conclude that the g function. So let's write this one. So we can write that here to be 5 for s minus 1 half, gamma of 1 minus s by 2 by gamma of s by 2, zeta of 1 minus s. Right? And suppose I want to see where it's vanishing, less than. So I have to see where it's right. Or sigma less than 0, but if sigma is less than 0, 1 minus s is at sigma larger than 1. So it's over here. So this guy is not. Gamma never vanishes. This also never vanishes. But this guy may have both. Right? If there is a pole over here, then it will be a 0 for this data. Right? So where are the poles of gamma s by 2? The poles are at s by 2 equals to 0, minus 1, 2, all the negative integers and 0. So s equals to 0, minus 2, minus 4, minus 6. All negative even integers will be the poles of gamma s by 2. So those are supposed to be the zeros of zeta s. For s equals to 0, I get zeta, which is a pole. So that 0 gets cancelled by this pole. There is no zero over here, but s equals to -2, -4, -8. All negative. If it is theta is vanishes. So we get that theta vanishes at -2, -4, -6, and these are the trivial series. So, okay, trivial zero of theta is over here, here, and nice things. So what is left now is what happens over here. And that is what is going on with the function inside where sigma is between 0 and 1. That's called the critical state. Alright. So why do we care what happens to the sigma beta function inside the critical state? In particular, where the zeros of this function are? That's because so we had this beta s as a product of the prime. So p means prime always. So I don't remember p prime. I'm going to one for this. First, so this beta is a nice analytic function from the demand. And then it follows from complex analysis that this beta function, maybe I should multiply let's multiply with gamma is by 2 and maybe with 1 in the whole. Huh? Better. So we have a x minus 1 here. Then this can also be written as a product over the zeros because complex analysis analytic functions are almost like polynomials. That's what was first found. And like polynomials, they can also be written in product over the zeros. Right? A polynomial, if there are any groups of the polynomial, then it's factorial is x minus plus 2 times x. So just like that, this guy, well, it's not a polynomial, but it behaves like a polynomial in that sense. So it will be like 1 minus this rho. So we need something for convergence, and there is a problem with something not that. Right? So there are two numbers a and b, so that product and written like this. But this rho runs over this is zeros. And we know that in fact it is zeros because all zeros of those are all accounted for over here. And there are other zeros inside the critical state that is also here. Right? So the zeta function in one part has this expression, which is called the Euler product, and also has this expression in terms of the zero, and it's called the other part. Right? Now you were interested in, or actually the was interested in understanding the prime numbers. And this equality gives that to understand the prime numbers, you need to understand this. In particular, if you want to make it explicit, take logarithm on both sides. So there will be a this sum, right, on the left, and sum over 0 on the right, and take derivative. So take the logarithmic derivative of that. If you look at the prime by t, yes, in one part there will be one expression will be a sum over prime, and another expression is, and so you can relate a sum over prime and sum over zero. In particular, you'll be able to relate 1 by p to the power s sum over prime, the this will appear over here with a sum over zeros, right? And there is one formula in complex analysis which is quite useful. It's called Perron formula. which says that if we have a sequence where n is a sequence of complex numbers, and if you're interested in summing the sequence up to some number of x, and let's x be not an integer, x is not a natural number, then this can be expressed in terms of the corresponding Dirichlet series. We form a Dirichlet series with this as the coefficients, the sequence of the coefficients, then x to the power x, s, take an integral 1 by 2 pi I, and this integral will be a vertical integral passing through our numbers. So this is integral, so take C something over here, and this is the integral here. This number, real number C. And this is the contour which starts at C minus I infinity. C plus C. This contour integral is equal to this. Right? If you are interested in counting the number of times less than equal to x, right? What you will be interested over here with the indicator function of the prime. Right? And then if you put the indicator function of primes over here for an, then you get 1 by 3 to the power s. So you get this series. Right? So that pi x will be a Heron formula, will be related to the integral of this Dirichlet series, and this Dirichlet series is related to the sum of zeros. So if you want to understand pi x, you have to know the limits. That is what Riemann observed. So this one, that was Riemann's observation, and he concluded from that you can show that when the solution has been down, there is a near part down the part. So that was the standard notation. If you can prove that that x is not equal to 0 for sigma, we know that it's not equal to 0 for sigma greater than 1. Suppose we can prove that it's not equal to 0 for sigma greater than 1, will vanishing on this line also, right? The age of the critical strip. From this will imply the pi x. That's it. This is the prime here, which Shlomo will prove on tour. So that's the basic. Everyone wrote an 8-page paper on this observation. That introduced the zeta function as a function of complex variable. He proved that it is a merely transform of a beta function. From that, he concluded that it has an application. He also concluded that it has an equation like this. He related that to the zeros of that beta function, and from there he derived what is called an explicit formula relating the prime over prime to zeros. And from there, he concluded that if you can say this for the zeros of the beta function, then you can improve the prime. So that was a long way. So that paper was written in 1860 something.
1859. 59. 96.
1896. Program was completed. On and delivered prove that data is okay. That of course, Riemann being Riemann, he said much more than this. He actually became more interested in this part than proving this one. Which is probably saying that if we realize that the zeros of any functions are more fundamental than the prime. Already a controversial statement. So Riemann started working on the zeros of the functions, and he conjectured, so that's how this is that theta s is not equal to 0 for sigma greater than 1 half. So if you draw this line to the center of 1 half, then there are no zeros for sigma greater than 1. Other math and derivative goes there are no zeros on line. And Riemann conjecture there are no zeros up to 1 half. And if you put this together with the functional equation, you can see that there will be no zeros on this side also. So there are no zeros. The only zeros will be those trivial zeros and the zeros lying on the central line. So that's a big Riemann hypothesis, and people are still trying to prove it. Now, so now if you prove this, then what you get? Of course, you get much more than prime number theorem. You can prove that pi x is almost same as lie x with an error which is like x to the power 1 half. Right? So what is lie x? Lie x is an integral 2 to x of d by log. It's logarithm. You know? So the first term of that mentioned of course. I'm not sure whether you know this notation. So this notation means that if you have a constant fx, we say that it's a equal x. That means it's a constant. So that the absolute value of x to the power eta, right? Is then equal to that constant. This constant doesn't affect x. So that's the meaning. So if you take pi x minus pi x, then there is a constant, because the difference is by that constant. Okay, I'll put actually for opposite epsilon is pi and pi. So they're like x by now. So there is a square root setting. Okay, so it will give you the ultimate prime number here. The number of primes is exactly like pi. Good. So what do you know about zeros? Almost nothing. It's yeah. So in the last 115 years, 16 years, after Riemann made that conjecture, almost nothing is known. But what happened? To solve it. So what's in deep? So now you're interested in the number of zeros in a critical state and where they align. And suppose one thing you want to do is to count height. So you go and take a rectangle of height t. So this point over here is half plus height t. And you can take the reflection which is half minus IT. Of course, the zeros over here, there's a symmetry. There's a number of zeros over here and the same number here. And then there is also a symmetry that the number of zeros over here and the same number over here. Okay, so every zero kind of counts with four four multiples of So NT is the number of zeros you're counting with the real part between 0 and 1 and the imaginary part between minus t and t is going towards infinity. Right? So you want to eventually count for this, and one can show that this is t by 2 pi log of t by 2 pi almost with an error of big O log. So they are exactly that many. That means there are quite a few zeros. Really. It's not only t, there are t times log t. So that means if you take a box of here, a box of with 1, then the density of zeros, the number of zeros in this box is measured. So that density actually compensates the sparseness of primes, because the number of primes is like x by log x. The density is like 1 by log x. So it's 2, which is the prime, which is the zeros, has the more big log. So it compensates that log. Okay. Sparse by a log, and this is dense by a log. So that is kind of matching. That should be matching. Yeah. So at least we know how many zeros will be there. Now, of course, your job will be to show that that exactly this many zeros on the same line. But proving this using complex analysis, you know the number of zeros of the function. The contour and the contour integral of the logarithmic derivative. So you take the logarithmic derivative of theta function and do a contour integral. But as long as the contour lies outside the critical state, you are fine because you know how it gets over here, how it gets over here. You cannot take the contour inside because inside you don't know much. That's the problem. Okay. And this part of this contour, this and this length compared to this length. So this part you can take care of. So that's why you'll be able to count the number of zeros in this big box. But if you want to take a small box over here, then that will be the whole contour should be inside it, where you don't have much. All right. So that's what. So he showed that there are quite a few zeros inside the box, inside the critical space. But now, how many? What about the zero to region? Can we show? So Riemann said there are no zeros on the right of 1/2. Can you show that there is no zeros on the right of 4? There's something called quasi-Riemann, and we prove something in that. That is still not known, but we can prove a zero to region, and the zero to region is like this. Okay. So here we will think usually at IT will be like 1 by of E or B. Sure. So you can prove that the sigma constant of T or two-thirds of T 1. So theta sigma of T is not equal to 0. Now, there exists a constant. Beta sigma plus IT not equal to 0. So this is, if you draw the picture of this sigma equal to this, you get a curve which looks like this. And this statement is saying that there are no zeros on the right of this curve. So this particular theorem was proved by no. And this still remains the record. Try to improve this to third with something smaller than that. Right? So that's about what I can say about the region where there are no zeros. We have the count for the number of zeros, have a picture of a region where there are no zeros. What else can you say? Okay, so there's a nice theorem which says that once you move away from the central line, you can expect no zeros by demand, but you can show that there are fewer zeros as you go towards the A. And that's called the zero density. It's called the zero fluidity. Okay? Okay. First statement goes back in half. Who showed so n sigma t. And guess what it means? Right? So this t is like that t over there. So sigma means you are looking at the zeros with the real part not the infinity. So this is my sigma, and then I'm looking at the number of zeros in these forms. Okay. So this is of course bigger than the zero for region, but smaller than the region given by Riemann. So here sigma is 1/2, and you can prove that this is bounded by e to the power effect 1 minus sigma minus sigma log e of pi. Total number of zero is almost like t log, right? And this is the number of zeros in this thinner rectangle, right? And now we'll see the exponent over here, right? That's the clever part of this theorem. So if you take sigma, say if you take sigma equals to 1 over here, what happens to the exponent? The 1 minus sigma becomes 0. Right? So it's kind of, the exponent is becoming smaller as you take sigma from 1/2 towards 1. So let's take sigma to be 4/5. Then what is this number? 3 times 1 minus sigma is 1/5. And 2 minus sigma is 6/5. Right? Right. Okay, my math here. This is 1/2. So that will mean that if you take this sigma to be 4/5, then the number of zeros on the right of 4/5 will be e to the power 1/2 instead of t log. Right? Some log. This is not that significant. What significant over here is this. So you get less and less zeros as you go towards the edge of the critical space. So that's why it's called the zero density. Right. So this is about the zeros which are not lying on the central line. What about the zeros which are lying on the central line? Riemann said they are all zeros are lying on the central line, but can you show that there are zeros lying on the central line? So that was proved by Hardy. Right? What Hardy proved was that beta has infinitely many critical bits. So he proved that beta half plus IP equals to 0 for infinitely many real. Okay. And then a few years later, with little loop, so RD little loop, they improved this result. They showed that if you count the number of zeros up to height t, then there are at least t many zeros, some possible. So total number of zeros is t log t, and they could prove that almost t many zeros are on the split group. Right, and so improve further by Sandborn, who showed that there are positive proportion of zeros lying on the 3D line. There are like t times log t times some constant and zeros lying on the 3D line. And this constant over here now is almost like 40%. So you can show that 42% of the zeros are lying on the central line, not all. At this matrix. Okay.
So, yeah, it's about 42 minutes till now. So you have time for about 18 minutes more.
Yes. Yeah. So now I want to relate zeros. So yeah, so this is the results about zeros of Riemann zeta function that we know so far. But there is another interesting problem of the Riemann zeta function, also related to zero, which is about finding out the size of the Riemann zeta function inside the critical space. So if you again say out of the critical space, say if you take sigma greater than 1, then you can prove that the zeta function is not growing at all. Because if you look at the Dirichlet series, right, it will be bounded by the value at the real number. So as you take t goes to infinity, it's not increasing, bounded by this value over here, right? But it changes as you go, as you take sigma equals to 1 or sigma less than 1. Okay. Then you can show that as you go up, it doesn't remain bound. It comes out. So then the question then arises, what is the growth? How fast can it grow? Right? So it's, and using the convexity principle from complex analysis, it is enough to answer the question for the central line. If you know the growth of the analytic function at the central line, since we know already the growth over here, you can use convexity to say about the growth anywhere in space. So you were interested in finding out what is the size of the Riemann zeta function at half plus RT as t goes to infinity. And from the functional equation, you can very easily show. So let me take t to be something large, n, for example. Then zeta half plus IT, there is an absolute constant over here, is bounded by that constant times t to the power 1/4 plus its size. Okay. Again, this notation, less is same as d. And says that something is bounded by something to the power something plus epsilon, means that this statement is true whatever epsilon you take as long as it's positive. So you can take epsilon to be as small as you want, say 1/3 something. But this entire constant over here will probably depend upon this epsilon. So as you take epsilon smaller, this entire constant may be lower. But that entire constant will no longer depend on t, only depend upon epsilon. So this follows from the functional equation. Now, Riemann hypothesis implies that the growth will be very small. So it is very slowly growing. So it will be going like for epsilon. So this follows from the Riemann hypothesis. So for any epsilon positive, the theta function is bound. Right? And this itself has a different name called the Lindelof hypothesis. And little would observe that this hypothesis actually follows from the Riemann hypothesis. In fact, you can give a much more precise sentence. You can show that the Lindelof hypothesis is equivalent to something about the zero. So one can prove that the Lindelof hypothesis is true even if the density of zero. If we take, so take, we're taking, we take a square like this is a square, so it looks like a square. IT, we take it as half plus IT and go up to half plus I equals 1. Okay, so this has this width is already 1, this height is also 1 over here. Then in this angle, this count, this will show that there are roughly like log p units. You expect all of them to lie on this line. That is, okay. And the Lindelof hypothesis is equivalent to the statement that the number of zeros not lying on this line, but outside this line, this one, is not big O of log p, but little o. So if you can show that the density is little o. Okay, what does it mean? Little of log p. It's like saying something in the middle of log p means that this by that is going to slip. So that means the density is pretty small when maybe like log p by log of p. Of course, you expect that it's zero. There are no zeros outside, right? Anyway, so the Lindelof hypothesis apparently, if you go to the corresponding zeros here, is much weaker. It's actually saying that you have to just turn one big O to a. That's so apparently is much weaker side, but most experts believe that people will improve Riemann hypothesis before proving it. So it's expected. So all right, yeah. So I wanted to mention this because of this work. Okay. So there's a huge gap between what comes trivially from complex analysis and equation and what is it, right? 1/4 goes down to 0. And so you may ask, so this is something where, analytic number theory is happy to work on. Reduce an exponent from 1/4 and see how far it goes, right? And that's for the subconvex. So to show that theta of plus IP, the identity by K is bounded by T or 1/4 minus delta. Breaking the context. The serial bound is not context. And that was first done by Weil. Actually, it was done by Harvey Blue using a method of Weil, where it came to be known as a Weil bound. So there's a curious story that Little announced this proceedings of the London Mathematical Society, where he and Hardy had proved something. So they claim that they have proved data output IP is in fact bounded by 50 power 1/6 plus epsilon, so 4. So that's just how come we found. So little node analysis is just so today. They claim that it has proved it the party, but he didn't publish it. So, but and then I think this first book was published by Landau, like 10 years ago. But of course, Landau says that the proof is basically the one. And so this was back 100 old, early 1918 something. And in the last 100 years, we of course improved this and really try to improve it. Ask me why. What we do. One, whatever we want to do. So yeah, but the improvement is very small. So the best known is 169. Okay. This is digital graph from 1917. Sorry, wait a second. I was still in the century. This is from 19. It's of course between there were many improvements of this. Anyway, of course, this also has something to do with the video. And this was from by income. So back to 20th century, early 20th century. So what did Income have to prove? Income proved that if you have this amount, C, so if this is true, then this implies something about the zero density. Then the number of zeros of almost like t on the right is bounded by e to the power times 1 plus twice c sigma of pi. Add over here. The exponent is different. And so if you look at this, and if you take say c equals to epsilon, so c is almost like 0, then if you plug in over 0 over here, then you have two exponents. That's something that we will really want. Then want to have something like 1 minus sigma times. Right? That will really prove that there is no almost no zeros somewhere. Right? So this he used to prove another previous thing. So that is now we're going back to prime numbers. So there are many problems with prime numbers. There are several problems of prime numbers, and there are 4 of them are quite big. One problem is a twin prime problem. What you can touch it now, it's almost like twin prime, not a twin prime. Then there is the problem of writing numbers as some of the primes. Okay, that's a good box. And then there is this problem about gap in time. There is this thing about Bertrand, and if you take an integer, go to the double of and then there will be a prime between it and what about instead of a, take n squared and go to the next one. So previously, if you start from n and go to 2n, this length is also n. So this is quite big compared to this current point. Start at n square and go to n plus 1 square, the length over here is 2n plus 1, which is much smaller than this current. So you're taking a very short gap. So you may realize it, start from n and go to n plus we call theta. And you want to see whether there is a prime. Button says there is a prime. The conjecture is there is a prime between n square. Right? Prove that is one of Landau's core problems. And but you can, of course, try to prove something like that. So that is n, go to n plus theta, and show that there is a prime in between with theta as small as possible. Okay, with the hope of getting theta equal to 1/2. When getting theta equal to 1/2 will be doing this, right? So you have proof that if you have this boundary, you get this digital, and together you I can say that this so it said 4% together shows that there is a prime, so that is prime between n or theta with theta equals to 1 plus 4, like 2 plus 4. Okay. So if you're lucky, near life and it looks equal to 0, then of 1/2. It is. So that means if you have a very strong bond over here, then you can reduce this and get a prime plus. Right? But if you take even if you take theta equals to 1/4, it will give you something. Again, theta equals to 1/4, what get theta to be? Let's see if you 1/4. So this is 1/4, so that means it's 2, and 1/4 is 3. So this between n and n plus into the power third is going to be the prime. It's already much stronger than 1. Okay, so that's convex. And you can plug in this on the Boolean and see that you get it. But you're still far away from what do you want?
Half. Half.
Half, yeah. But when Ilham wrote this paper, then the best form was almost like 1/6. Everything is better than 1/6. So if you take 1/6 over here, then you get theta to be 1/6 is what? 2/3 has to be 5/3. Third and fifth. 8/3.
8/3.
8/3. 5 by 8.
Yes.
That will prove that if you start from Q and go to input 1 Q, and the length is like 3 square, right?
Yes.
Then between these two, there is a prime. Between two constituent Q, it's prime. That follows from. That doesn't follow from this one. This just fits. Because this length is n squared, and n squared is q to the power. So this length is theta equals to 2/3. So this convexity distance that is upon this part, the prime. And that also has some. Yeah. Okay. All right. Yeah. Maybe in the last few minutes, I will just mention about their function. The reason I said that zeros are more fundamental than prime that you can relate the zeros with more and a lot of other arithmetic objects on the class. And one example which probably not be covered is study modular forms.
It's not
Covered. So if you study modular forms, then at least I can mention this problem. Look at the simple x square plus y square plus z square equal n. So you're writing an integer sum of p squares. Not all integers can be a sum of p square. For example, 7. Anything which is congruent to 7 1 almost everything else can be written as sum. So take n not congruent to 7 minus 8. Then you can and then you can show that in that case there are a lot of representations. They're like roughly root n many. Roughly root n many solutions. Okay, so let me draw a picture over here. Yeah. Okay, so you're taking a huge sphere here. This expression y b. Right? So this is the sphere. That's so then and then on this sphere, getting many points. Okay. So I'm solving over integers x, y, z. So we are getting this many integers, this many points over here of radius 10, and then we project it down to the empty sphere. Okay. So as n becomes larger, you get more and more points on this image, and many points. And we want to know how they get it. And Lilly conjectured that they get it. So that will mean that if you take a small region over here, omega say, if you count the number of integers falling inside there, yes, divide by the number of count, that will convert to the measure of this region you put uniform probability. So that's called the uniform. That was Lilly's conjecture, and this can be related to a complexity problem of this the modular form by Richter character or a character. So you have to show that this you need a bound of this, so the t is 0 over here, n is valid, and there is a corresponding problem. Here I said the problem here. There is also a problem the level aspect here. And if you can prove a subconvex form, again there is a functional equation, and from the functional equation you have a complexity. Complexity bound is not good, but any subconvex form here, you know that forms. So this is some problem which has nothing to do with state, but it's related to the size of the electron. And as I say, the size of the electron is also related to the zeros. So the zeros are related to something which are not primes. But anyway, we know that the zeros and primes are like dually related to each other. So thinking about this can be translated to say something about primes. So at the end, this is also going to be translated over something primes. In itself,